Okay, good morning, and welcome back again to Algebra 1 today. As you probably figured out, I am still not quite feeling great. I'm still feeling pretty under the weather, and rather than risk it and coming into class and getting all you guys sick, I'm here with my dogs and recording another video for you. So what we'll do is two things, I believe, today. For those of you guys that are in the 1A section that I teach, you will be taking the STAR test and then working through kind of the notes and the exploration here for lesson 1.3. If you're watching this video, you should have already completed the STAR testing if you're my 1A students. If you are my B-Day students in my 3B section, you should have completed STAR testing. I believe it would be on Monday the 18th. So if you're in the B-Day students, you're good to go. You can watch the video and go from there into some practice to work on the Ready, Set, Go problems. If you're part of my A-Day students, you'll have taken the STAR test. You'll be working through the exploration and the notes today, and you should still have a little bit of time to finish out the practice problems for the Ready, Set, Go as well once you get towards the end of the recorded lesson. As we get rolling into our time for today, make sure that you are turning in your phone to the wooden phone caddy. The sub has notes to make sure that phones are collected at the beginning of class. In the last like 5-10 minutes or so of class, you're welcome to go grab them again. But if you need the numbered slot assignments, you have them up here on the screen. So make sure that you're putting phones away as we're getting started today. Make sure that you pull any earbuds out of your ears or headphones. Make sure that you put away smartwatches and devices as we get moving into our time for our lesson today. What I want to do is get into the notes today in the section for 1.3. The notes for 1.3, which are titled Growing Dots. I want you to find these problems that are part of the retrieval problems, which might be a little bit later in the notes section. And I want you to try and answer these questions as you see them. So you'll notice here that we have two tables of values. For this one on the left, we're using that table of values to say find f of 1 or f of -2. We're trying to find x for when f of x is equal to 1, and we're trying to figure out if x equals 2, then what is f of x minus 1. For this table on the right, you're going to be told that g of x is equal to -4 to the x power. And you're trying to determine some of those outputs, some of those g of x values when they tell you the inputs, the x values. So a little review of some things that you've probably spent a lot of time on in middle school. Might be a little bit rusty, and that's okay. I want you and your group mates to try these. These should be found in the retrieval section of your notes. And in maybe about like 3 to 5 minutes or so, I want you to unpause the video and we'll kind of talk about these problems and touch base from there. All right. So these are the retrieval problems that are a little bit further towards the end of our notes in section 1.3. We're kind of reviewing some topics in algebra that you guys spent a little bit of time playing with, maybe in middle school. Really what we're doing is kind of reviewing something called function notation, which we've also played a little bit with in our lesson for 1.2, our lesson on growing dots. But you may notice something about how the values are changing in our tables, and that might maybe change the way that you're trying to evaluate them, especially for that guy on the right-hand side. Now, on the left-hand side, they ask us to find something like f of 1 or f of -2. And what I want you to notice here is that x is our inputs, also known as our independent variable on the left-hand side of the table, and f of x are our outputs, also known as our dependent variable on the right-hand side of the table. So when x is a certain value, f of that value is a different number. And what we're trying to do here is figure out, say, f of 1 or f of -2. So if in function notation we usually see f of x, and here they've written f of 1, it means that we're doing x equals 1, and we're trying to find the output. So in this particular instance, if x equals 1, I'm going to see here that f of 1 is equal to -13. It's the corresponding output for that given input. Very similarly, if I'm looking for f of -2, then I've swapped out x equals -2 here, and I'm trying to find its y value. So in this case, that corresponds to an 8. Where it gets a little bit different is when you take a look at these other two questions. They say find x for when f of x is equal to 1. That's slightly different in the notation. When f of x is equal to 1, notice here we're kind of working backwards to figure out that x, the input, must have been -1. And that's kind of tricky, right? We'll play with that idea more of kind of reversing that process and solving as we get further into some of the algebra material this year. Similarly, for number 4, if they say if x equals 2, then what is f of x minus 1? Well, let's think about x minus 1 first. If x is equal to 2, then x minus 1 is 1. So if I'm trying to figure out f of 1, then I'm going to see here that that's really equal to -13. So if I were to write this out, I could say like if x is 2, then f of x minus 1 is like 2 minus 1. That's the same thing as f of 1. And there's my output -13 there for my final answer. So just some review of notation in this case. And again, we spent a little bit of time sort of playing with function notation when we were working with our lesson in 1.2. You've probably seen a little bit of this since middle school or so in pre-algebra, but it's nice to continue just to working out these examples and getting comfortable with it. Now, on the right-hand side of the screen, you will see a table of values that's not complete yet. They give us a bunch of inputs for x, and they want us to find the outputs, and they give us this sort of like function rule. They say g of x, this function of x, is equal to -4 to the x power. Now, one thing that might be kind of helpful when you're working out this table is maybe to start when x equals 1 and then x equals 2. If I think about, say, I don't know, -4 to the first power or -4 to the second power, we can maybe use this to develop a way of figuring out the rest of the table that might help us understand what it means to do like -4 to the 0th power, which is kind of an odd thing to think about. If I say -4 to the second, what I want you to think about real quick is what does that really mean? If I give, say, -4 that exponent of 2, that's like saying that I'm taking -4 and I'm multiplying it by itself, right? And if I do -4 times -4, the 4 times 4 is going to become 16, but what's a negative times a negative? Well, that comes out positive, right? So if I want the answer to -4 squared, I'm going to see there that that's positive 16. Now, if I do -4 to the first power, it's essentially like I'm just saying -4, right? He doesn't have anybody to multiply with, so in that particular instance, nothing really interesting happens. But if I think about -4 to the third power, well, that's like -4 times -4 times -4, right? And in this particular instance, 4 times 4 is 16, but then 16 times 4 is 64. But let's now focus on the negatives, right? A negative times a negative is a positive, but what's a positive times a negative? So that result kind of switches back to being negative. And if I think about, say, -4 to the fourth power, well, we're kind of like daisy chaining these things together, right? That's like -4 times itself 4 times here. Now, -4 times -4 is 16, so you can think of this as like 16 times 16. We're going to have a pretty big number there, right? I think if memory serves there, that should be 128. Now, what I want you to notice is as you take a look at the table, and this is kind of reviewing one of the things that we saw back maybe in our retrieval problems for lesson 1.2, to go from -4 to 16, or from 16 to -64, or -64 to 128, you might notice something about that sequence. To go from 4 to 16, it looks like we're multiplying by 4. To go from 16 to 64, it looks like we're multiplying by 4. And to go from 64 to, oh, it won't be 128, will it? It'll be something more like 256 there. There we go. You're also going to be doing another multiplication by 4. But to go from negative to positive, and to go from positive to negative, and to go from negative to positive, and to go from positive to negative, what you might notice here is that you're repeatedly multiplying by a -4. as you go forward in the sequence. Now, thinking of something to the zero power is kind of a strange thing because it's like you're saying you're taking it and multiplying it by itself zero times, right? And a lot of people kind of struggle with what that's supposed to look like. What I want you to think about here in the table is if instead of going forwards, you were going backwards, what do you notice you do to say 256 to get 64? Or what do you do to 64 to get 16? Or to go from 16 to 4? You may notice in that case that you're dividing, right? And in particular, to go from, say, positives to negatives and negatives to positives, we're going to be dividing by -4. So if we wanted to figure out a way to figure out what -4 to the zero power is, well, you could do -4 divided by itself, and what you'll see there is that you just get 1. So -4 to the zero is just 1. And you'll start to see that a little bit more in Algebra 1 as we practice with like exponent properties that it turns out anything to the zero is really a 1 because you'll always do that something divided by itself step to get back to that value in the sequence. So again, these are the retrieval problems for 1.3. They're just there to kind of get the gears turning, getting us thinking about number sense, thinking about function notation, getting some practice, kind of reviewing how sequences change. As we get ready to launch into our lesson today for 1.3, I want you guys to try this real quick. At the beginning of lesson 1.3, you're going to be given these 5 statements, and you're going to be asked to justify which of these 5 doesn't belong with the rest. So I want you to go ahead and pause the video. I want you to discuss with your group mates which of these do you think is different and doesn't belong, and why do you think that's the case? Okay. So you've had maybe a couple of minutes with your group mates to sort of mull this one over and think about some of these expressions. We're trying to ask ourselves which one doesn't belong. And we're trying to think about a way to make that argument that justifies our choice to other people. There's not just necessarily one correct answer to this particular question. You may notice that some of these are written as just a lot of numbers multiplied together. Some of these have exponents. Some of these have the same numbers that are multiplying together, and some of them look kind of a little bit different. You may notice a lot of different ways to make the argument that there's something in here that doesn't belong. I would say maybe that one thing that stands out to me is that statement C doesn't seem like it belongs. And the reason for me that C doesn't really match with the rest of them is I see that 1/2 to the second kind of flying around. Now, if I think about what 1/2 to the second looks like, that's like a half times a half. And that's kind of a weird one to think about, right? If I have an object and I take half of it, but then I take that half of an object and take half of that as well, ultimately what I'm left with is just a quarter of my object, right? So I'm dealing with a fraction there where a half squared's like a fourth and nothing else has a fraction. So that one seems a little tricky. It seems different, right? Now, maybe another thing that you noticed is that, say, on this guy, statement D, he's written as 16 times 10, where there's no 5 and there's no 2, and that seems to be a component of, say, like statements A and B, where there's 5 and 2. Another thing that you may be arguing is that if you take a look at statement B or statement C, they have exponents where everything else doesn't. So statement A is just a lot of numbers multiplying together, and B is like a super condensed form of that. Statement E is 20 times 2 times 2 times 2. D is 16 times 10. One thing that I want you to think about here, though, is really what does it mean to take something to a power? Well, if I think of 2 to the 5th, that's essentially saying take 2 and multiply it by itself 5 times in a row, right? So statements A and B are equivalent in the sense that they're really trying to say the same thing. They just look kind of different. But then that sort of leads us into the question, well, what about C, D, and E? Are those really going to be the same thing as, say, statements A and B? Now, one thing that you could think about is if you're looking at, say, the number 20, you can sort of break that down into a list of factors. You could say that 20 is equal to 2 times 10. But then I want you to think about 10. What could you write that as? Well, you could write that as 2 times 5. So one way to break down 20 is to say that that's like 5 times 2 times 2. But if you think of it that way, then statement E is like 5 times 2 times 2 times 2 times 2 times 2. So is statement E really any different than statements A and B? If you're looking at statement D, one thing that you may be thinking about is, okay, well, what about 16 and 10? Can we sort of break those numbers down in a similar way? So I could say 16 is like 2 times 8, and then 8's like 2 times 4, and 4 is like 2 times 2. And then I could think of 10 as like 2 times 5, right? This method of sort of breaking these guys down is what we call prime factorization, where a factor is just something that multiplies by something else to get us the number that we started with. You could write 16 as 2 times 2 times 2 times 2, and you could write 10 as 2 times 5. So this is really the same thing as 2 times 2 times 2 times 2 times 2 times 5, but is that really any different than statements A, B, or E? They're kind of equivalent, right? Now, that sort of leads us here to statement C, where maybe I want to think about that 128 and that half to the second, right? We already know that half to the second is the same thing as 1/2 times 1/2, which is 1/4, right? But let's think about a prime factorization for 128. If I take 128 and I wanted to break it down into a prime factorization, I want to think about a small number that divides evenly or nicely into it, like 2. Well, 2 times 64 would get me back to 128, but then I can do the same thing for 64 and say it's like 2 times 32, right? From there, I could go even further and say that 16 in this case, or rather 32 rather, is going to be like 2 times 16. And then I could say 16 is like 2 times 8, and I could say 8's like 2 times 4, right? And 4 is 2 times 2. So 128 is really 2 times 2 times 2 times 2 times 2 times 2 times 2. And that's a lot of 2's to multiply, so I might write that as like 2 to the 7th. But from there, one thing that I can think about is, well, a half to the second is like a fourth. And a fourth is like 1 over 2 squared. So some of you guys may have been sort of exploring like the numerical value of these expressions. And maybe you notice that if 128 is 2 to the 7th and a half squared is like 1 over 4, which is 1 over 2 to the second, then you could say 2 to the 7th over 2 to the second is a fraction that's going to simplify. Now, this is kind of just some number review. So if maybe you weren't making this argument, I wouldn't fret. But we know 2 to the 7th is just 2 times itself 7 times in a row. 1, 2, 3, 4, 5, 6, 7. And 2 squared is like 2 times itself. So if I do 2 divided by itself, that kind of cancels and leaves behind a 1, right? And then I'd have 2 to the fifths in the numerator and 1 in the denominator. So really, they're all equivalent statements. They're all expressing the same numerical value. They're just kind of looking different. But really, the point of this exercise is to think of a way to justify why we think something doesn't fit with the rest. So just kind of a nice little warm up in the sense that we just get a little number practice there with exponents and what they're really trying to say to the reader. As we go into our lesson for today, we're going to do our first common formative assessment about August the 26th to the 27th to see how things are going, some of the basics from Unit 1. We're going to take our first summative assessment, our kind of first unit test for Unit 1 on September the 4th or the 5th, depending on whether you're on an A-day or a B-day schedule there. For those of you guys that are in my 1A class, given that I'm out, you guys should have already taken STAR testing. So now we're in the second half of class. We're going to wrap up the notes for 1.3. If you're in my 3B section, you took the STAR test with the sub on August the 18th there, so you should be good to go. In which case, you'll have a nice chunk of work time to work through some of the Ready, Set, Go problems. But either way, what we've got for our time today is our second lesson of Unit 1, where we're talking about another pattern of change in which we're looking at growing patterns of dots. But you may notice something a little bit different compared to what we saw last time. Our goal is to understand and kind of define this notion of what we call a geometric sequence and a common ratio. We're going to do that in much the same way as we did in lesson 1.2, where we're sort of talking about ways to encapsulate a pattern of change, how to represent that. So we're going to be building tables and graphs and trying to write some equations. We're going to sort of review this notion of recursive versus explicit thinking. But we're going to sort of compare and contrast what we see compared to the lesson for 1.2, where we're defining this idea of an arithmetic sequence. Now, the big takeaways from our last lesson is that an arithmetic sequence is still a sequence of numbers. It's just that when you look at the outputs of the sequence, so for example, 1, 5, 9, 13, and 17, the pattern of change between them is just adding or subtracting a constant. So to go from 1 to 5, or from 5 to 9, or from 9 to 13, you're going to notice here that you're just adding 4 every time. When we're talking about a sequence, we always have a first term in the sequence. So that was like having the 1 dot in the beginning. And then we were adding 4 dots on the outer layer over and over and over again. So this sequence would represent the total number of dots per minute that goes by in that process. The other thing that we talked about is that there's not just one way to represent a sequence. We used a table of values where we said in the beginning, there's the 1 dot, so 0 minutes into the process. And then 1 minute into the process, there's 5 dots. 2 minutes into the process, there's 9 dots, so on and so forth. The nice thing about the table is it kind of gives us a way to take these values as sort of like coordinate pairs and put them down on a graph. So in this graph, on the x-axis or the horizontal axis, I have the number of minutes that have gone by. And on the y-axis or the vertical axis, I have the number of dots in the pattern. What you'll notice is that the very first dot on the graph I've drawn in blue, it's the same thing as like that first column in this table where at 0 minutes into the process, I have 1 dot. That's like the y-intercept of the graph. It's where that pattern is going to be crossing that y-axis. We defined time as being the independent variable, and the number of dots as being what we call the dependent variable. The number of dots changes because time changes, not the other way around. Now, we also defined this idea of recursive versus explicit thinking. When you were looking at the pattern, what you may have noticed is that if you knew what the last pattern was and you added 4 dots to it, you got the next one. Some students were thinking about that a little differently, though. They were saying, well, you always have 1 dot, but then you need to add to that 4 dots times the number of minutes that have gone by. And that's an example of what we call more explicit thinking. So in explicit thinking, we use something like function notation where we say f of t, the number of dots t minutes in the future, is going to be equal to some kind of function rule. So in this case, 4 times t plus 1, where t is just the number of minutes that have gone by. We call that the input of the function. They're both useful, and we both use them to talk about these sort of patterns of changes. They have strengths and weaknesses. They have benefits, drawbacks. Now, as we go into our time for today, we're going to sort of take the same strategies, the same way of thinking about a pattern of change, and apply it to a new scenario. So in the notes for section 1.3, growing dots, I want you to take a look at this diagram in the launch section. I'm going to give you a pattern of dots where I say that there's this many at the beginning, and then every minute that goes by, you might be noticing that the pattern is shifting or changing in some fashion. So I want you to take a look at the diagram and then mark it and discuss with your group mates, how do you see the pattern changing? So go ahead and pause the video for a minute. I want you to discuss and think about, what do you notice as far as how things are changing here? All right, so as we kind of launch into our activity for today, we have a sequence of patterns of dots where it's changing after every minute. And what I wanted you guys to do was just to kind of take a moment and discuss and maybe like mark or highlight the diagram in some way in which you see the pattern of the dots changing. The way that I was looking at this, and the way that maybe some of you guys saw this as well, is that at the beginning, we have these three dots in sort of a triangular configuration, right? And then at the 1 minute mark, I have two dots in each of these three different groups in this sort of like triangular looking shape. And then 2 minutes later, I've got four dots in these three different groups. So if you think about it and you kind of break it down into like groupings, one thing that you may have noticed is that you have three groups at all times, and the number of dots in each of those groups is changing. So maybe you were sort of recognizing that pattern of change if you're looking at it that way. Now, another way that you could maybe have been looking at this, and one that occurred to me, and maybe some of you guys as well, is well, if you take a look at the diagram for the 1 minute mark, you'll see the former diagram from, say, the beginning. It's just on top of that old diagram, you've added a dot. And if you look at the 2 minute diagram, you'll see that you have sort of like the 1 minute diagram still there. It's just that inside that grouping, you sort of like doubled the number of dots that you had there. And same thing at the 3 minute mark, right? If you take a look at the 3 minute mark, you have the same diagram from the 2 minute mark. You've just taken it and you've doubled it. So one thing that you may notice as we take a look at this diagram is that the number of dots is changing not by like adding a certain amount, but maybe by multiplying by something. And there's maybe a lot of different ways that you could see how this pattern is changing. These are just a couple of ways they may have potentially been looking at it. So as we go from here, what I want you to do with your group mates is try and figure out how many dots there's going to be at the 5 minute mark. So assuming this pattern of change is going to continue the same way from the beginning until the 5 minute mark, how many dots do you think there are going to be? And then I want you to keep going from there. I want you to try and develop some models, like a table of values, a graph, and then maybe from there even some equations to help you understand how this pattern is changing, and we'll bring it back together from there. So to begin, how many dots are you going to have at the 5 minute mark? And then from there, some different representations that might help us develop a couple of equations that could be useful here. So what I'm going to notice is if I'm taking a look at, say, like the number of dots in each of these diagrams, I go from 3 dots to 6 dots to 12 dots to 24 dots to 48 dots, right? And I want to draw maybe a diagram that's going to be representing what happens at 5 minutes into the process. Now, if you were looking at this and thinking about how the next diagram contains the last diagram, but it's twice as many, one thing that you could be doing here is saying, okay, well, for the 5 minute diagram, I've got to draw what I saw for the 4 minute diagram. So in one grouping, I've got to draw like a little 4 by 4 square of dots, but I then need to take that and I need to double it, right? So for say the top part of my diagram, it might have two 4 by 4 squares of dots. And that would only be one such group that I would need to draw two more times to get the full diagram, right? What you'll notice is that that's going to take a while because there's just so many dots that you have to draw out in that process. But maybe a different way to think about it is, okay, well, if I've got, say, something like 4, 8, 12, 16 dots in each group, then that means this group is going to have 32 dots. And if I have three groups of 32 dots, then however I figured out my pattern, I should see at the end of 5 minutes something like 64 plus should be like 96 dots in that case, right? Which is twice as many as 48. That's maybe one way to look at it. Another thing that you may have noticed is that if you think about how things are changing in each individual group as the minutes go by, there's always three groups, but say at like the 4 minute mark, right? You have this like 4 by 4 square. At the 3 minute mark, you have like this 2 by 4 square. You can sort of count the numbers in those groups and then triple it and work with it that way. There's a lot of ways you could potentially get an answer here, but we're going to see that there's 96 dots that get involved in that fifth diagram. Now, going on to the next slide here and getting into problem 3, where we're trying to come up with multiple representations. Let's say in our table of values that on the leftmost column, we're tracking the amount of time that's gone by in minutes for the process. And in the rightmost column, we're tracking the number of dots. Now, this leftmost column, kind of like we talked about in our last lesson, that's going to be our independent variable, time in this case, because the number of dots changes depending on time, not the other way around. And this rightmost column is going to be our dependent variable. It's the number of dots. I've noticed that at the 1 minute mark, I have 6 dots. At the 2 minute mark, I have 12 dots. At the 3 minute mark, I've got something like 24 dots. And at the 4 minute mark, I've got 48 dots. Now, if I wanted to figure out how to represent this at the beginning piece for the pattern, I know I've got 3 dots. But how many minutes have gone by if we just started the process? In that case, we've done 0 minutes, right? Now, I did that in a different color because I want to kind of keep that separate when I'm thinking about the graph of this table of values. One thing that I might do for my graph is, because I don't have any axes drawn yet, I might take a minute to sort of draw a vertical axis and a horizontal axis here. So the horizontal axis on a graph we reserve for our independent variable, which is going to be, in this case, time measured in minutes. On the vertical axis, we're going to track our dependent variable, which in this case is the number of dots in the pattern. I want to try and break this up in such a way that I can capture all these number of dots that I see in the table. So I got to think ahead a little bit about how to space out, say, the values on the vertical axis in terms of these tick marks and the values on the x-axis. So as I'm counting up the y-axis, I'm going to notice that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, maybe like 16 or so tick marks. So I might represent this like very topmost one as being 48. And then if I go 1, 2, 3, 4, 5, 6, 7, 8 tick marks down from there, that might be my marking for 24. And then down here at the very bottom where my axes intersect, I'm going to let that represent 0 dots. Now, I don't have 0 dots, but I'm just putting it there so I know that that's like what that y value is going to start at. Halfway between 0 and 24, I can put down a marking for 12. Halfway between 24 and 48, I could put down a marking for 36. I think what I'll maybe do from there is I'm going to count by 4s going from left to right. 1, 2, 3, 4. 1, 2, 3, 4. Just so that I have enough space to kind of put all these down and have a nice, clean, easy to read graph. You don't necessarily have to space it the same way that I did. But taking a moment to sort of think about how they might space out at first is going to be helpful, just to make sure that we have an easy to read graph. Now, based on this spacing in the vertical axis, what you're going to notice is that each tick mark is going to represent 3 dots. So I'll go up 3, 6, 9, 12, 15, 18, 21, 24. So if I wanted to put down my first mark for my graph at time 0 and 3 dots, I'm not going left or right at all from the origin, but I am going up 1 tick mark, and that's going to be like my first marking for my graph. From there, when I go 1 minute in the future, so I'm going to go right 1, which is 4 spaces on that horizontal axis, I'm going to go up to the marking for 12 dots on the vertical axis and put down a coordinate. I'm sorry, for 6 dots rather. There we go. But I'm going to follow that process, right? As I go from the 1 minute mark to the 2 minute mark. So I go over to the 2 minute mark on the horizontal axis. I go up to the 12 minute mark on the vertical axis. I put down a dot there, and I keep up the process, right? So at the 3-minute mark, I'm up to 24 dots. And then at the 4-minute mark, I'm going to be up to 48 dots in this case. Now, one thing that I want you to think about real quick here is how this is similar, but also how this is different to the graph that we drew on lesson 1.2. There's still like this y-intercept term that I drew in red, which is essentially where our sequence is crossing or touching the vertical axis in some fashion, right? And that corresponds to like a coordinate here of 0, 3. So the input variable is nothing, and that's why it's on that vertical axis, but the output variable is 3. We still have that, and we're still representing the change with these like dots on the chart, but are you going up the same number of units every single time? Instead of like adding a certain number of units at a time, what you're going to notice is that whatever the old output was, you're multiplying by 2 to get the next one. So to go from 3 to 6, I multiply by 2. To go from 6 to 12, I multiply by 2. To go from 12 to 24, I multiply by 2, so on and so forth. But notice on the graph that that means I go up 1 mark at first, and then I go up 2 marks at first, and then I go up 4 marks, and then I go up 8 markings. So these values on my graph are not going to fit on a straight line anymore, right? They're going to fit more on like a curve in this instance. And that's going to be a kind of non-linear pattern of change. So instead of adding or subtracting by the same amount, it's actually that I'm doubling by a certain value. So I'm multiplying by 2 to go from the last output to the next one. So as we wrap things up here, I want to try and come up with an equation, right, to represent how I think things are changing. If I'm thinking about this in more of a recursive way, and by recursion, I mean that if I want to get like the next number of dots based off of what I knew what the previous number was, what is it that I'm always doing to the previous output to get the next one? I'm just sort of multiplying by 2, right? So if I wanted to figure out, say, the number of dots 5 minutes in the future, I take the number of dots at 4 minutes and I double it. If I want to get the number of dots 6 minutes into the future, I take the number at 5 minutes and I double it. So if I wanted to go step by step in the table, I can sort of use this pattern and get to an answer eventually, but it might take a minute to get there, right? If I was thinking about this in maybe a more explicit fashion, one thing that I want you to notice is if you focus on only like one group at a time, the number of dots in that group is doubling. So I go from 1 to 2 to 4 to 8 to 16, right? Now, if I think of 4 and I think of 2 and I think of 8, I think of 16, those are all like 2 times itself a certain number of times, right? 4 is like 2 times itself. So it's like 2 to the second. 8 is like 2 times 2 times 2, which is like 2 to the third. And 16 is like 2 times 2 times 2 times 2, which is like 2 to the fourth, right? Notice that the power is equal to the number of minutes that have gone by. So if I wanted to write an explicit equation, I could say maybe something like the number of dots is equal to 2 times itself over and over, but maybe a more efficient way is to say it's like 2 to the power of the number of minutes that have gone by. But I won't quite get the right answer if I do only that, right? I've also got to account for the fact that every single one of these is in 3 groups. So I'm doubling, but I got to capture that 3 group pattern of behavior. So I'm going to take whatever I get for 2 to the power of number of minutes, and I'm going to triple it. And that might give me my final equation. Now, if I wanted to write that perhaps in function notation, one way that I could do it is say like d of t, so the number of dots versus time measured in minutes is equal to 3 times 2 to the t, where t is the number of minutes once again. I could do it that way. Or maybe instead of d of t, I could use like f of t if I wanted to use maybe more formal function notation. So f of t would be the number of dots and t would be the number of minutes. If I sort of check against my table, kind of similar to how we did our retrieval problems, I'm going to notice that I get the right number of dots there because I captured that doubling pattern and I captured the fact that I have three groups that are doubling. So what I want you to think about here is if I wanted to put this into motion, say with a different pattern, before we sort of formalize and define our findings before we get into some practice today. Let's say that I have this diagram for the 1 minute, the 2 minute, and the 3 minute mark. How would you write a recursive and an explicit equation for this scenario? So go ahead and take a minute with your group's mates, maybe a minute or two to try this, and then we'll carry on from there. So one thing that I'm noticing here is kind of similar to our earlier problem. I have three groups in each of my diagrams. So maybe one thing that I'll do is kind of focus on one group at a time and then consider what having three of these groups means in the next step. But inside of each of these groups, I'm going to only count the number of dots I see. So at the 1 minute mark, I have 1 dot. At the 2 minute mark, I have 2 dots. And at the 3 minute mark, I have 4 dots. Now, 2 and 4, those could be written as like 2 to a power. If I wanted to carry this out to the 4 minute mark, what I'd see is that in that upper group, I'd have 8 dots, but I'd have 3 groups of it. So if I think of 2 and 4 and 8, I can express those as 2 times itself a certain number of times, over and over and over again. So one thing that I might think about here is the fact that I'm having 2 to a certain number of powers, but it's not exactly the same as the number of minutes that have gone by anymore, right? At the 2 minute mark, I have just 2. At the 3 minute mark, I have 2 times 2. At, say, the 4 minute mark, I have 2 times 2 times 2. So my explicit equation here might look a little different. Here, what I'm going to notice is that I could say that f of t is still going to be like 2 to the t somehow, but I've got to take away 1 from the number of minutes to get the right exponent. So maybe I write this as 2 to the t minus 1 power. Now, I still have 3 groups in each diagram. So if f of t represents the number of dots, I've got to take 2 to the t minus 1, and I've got to multiply it by 3 again. Now, if I'm thinking about this recursively, what I could say is that the next number of dots is equal to the previous number of dots in the pattern times 2. So the recursive equation here is really no different than what I saw in the last scenario. In this particular instance, right, if I wanted to work backwards to figure out what I'd have at 0 minutes, you may notice that you go from 4 dots in a group to 2 dots in a group to 1 dot in a group going backwards. So if I were to think about undoing that, I might have no dots in a group, and that would be like my 0 minute mark. The at the beginning term just happens to be nothing in this case. But what we're really focusing on here is just kind of 2 ways of looking at the pattern, right? There's this recursive way where I'm using what I previously knew to get the next thing. And there's this more explicit way where I define an input and an output variable, and I can figure out the number of dots for any number of minutes that have gone by. So we're thinking strengths and weaknesses here, right? Now, in the takeaways section of the notes, here's where I want you guys to kind of record our key findings for today. We were talking about a sequence of dots, similar to how we did in 1.2, but what we noticed is that instead of adding by something over and over again to get the next thing, we were actually multiplying. And the fact that we were multiplying by something means that this is a different kind of sequence than an arithmetic sequence. We refer to this as a geometric sequence. So a geometric sequence is a sequence of numbers where instead of a common difference between the outputs, there's a common ratio. Instead of adding by a certain value, I was multiplying by a certain value to get the next one. Just like arithmetic sequences, geometric sequences have a first term, and then they follow this rule of the common ratio multiplying to get the next one in the sequence there. There's not just one way to represent these. We use tables of values, we use graphs, we use actual diagrams, we even use equations to represent these. Similar to arithmetic sequences, if we're thinking about a table and a graph, we might need to think about like going backwards instead of forwards to find like that y-intercept term. But we always want that term to make sure we know where that graph is going to cross that vertical axis. The other thing that I want you to notice here is that when we take our coordinates from the table of values, the input-output pairs, and we put it on the graph, they don't really fit on a straight line anymore. They fit more on a curve in this case, and that's one of the giveaways that you have a geometric versus an arithmetic sequence if you're looking at graphs. Finally, just like arithmetic sequences, we have recursive and explicit ways of writing an equation to try and represent the pattern of change. For recursion, instead of thinking about adding something to the previous diagram to get the next thing, we're multiplying by that common ratio term. So in this case, I could say that the next pattern was 2 times the previous pattern's number of dots. If I was thinking more about an explicit equation, I could say f of t, the number of dots versus time, is going to be equal to 3 times 2 to the tth power. Now, t as an exponent is just a way of kind of capturing that I'm doubling, I'm multiplying by 2 a certain number of times that depend on the number of minutes that have gone by. That 3 has to deal with the fact that I had 3 groups of dots in which that doubling pattern was occurring. So that common ratio serves as a base to a variable power, as opposed to like a number that's multiplying onto the variable like we saw with an arithmetic sequence. So as we wrap things up for our time today, what I want you to discuss with your group mates is kind of this last element of our lesson for today. How do you notice the outputs in the table of an arithmetic sequence are similar, but also different to what we're seeing with a geometric sequence? As we're wrapping up for today, this is just kind of a nice way to sort of encapsulate the similarities, but also the differences between these two lessons. I also want you to go ahead and get started on the Ready, Set, Go practice for our lesson 1.3 today. What I want you to do is take the time with your group mates to finish some of the practice problems for 1.2, as well as start some of the practice problems for 1.3. For the time being, we're going to assign all of the problems from the Ready, Set, Go in our last lesson and this lesson, but we're not necessarily going to do that all the way in the future. If you do have some questions on some of the Ready, Set, Go problems as we go, make sure to hold on to them. I'm hoping that I'll be back in the classroom very soon as I'm starting to feel better. I'd be more than happy to kind of go over some of our solutions there as time goes on. But for the time being, I want you to finish up with some of the Ready, Set, Go problems that you'll find in the notes for both of our lessons. Apart from that, I hope you guys have a great rest of your day, and I'll see you guys again soon.